Hello, I'm Robert Vandermeulen. I'm from University of Michigan. This is work I did with my advisor, Clayton Scott. Um, this is operator theoretic approach to non-parametric mixture models, which is a mouthful. Basically, it's a different way to look at mixture models. So a mixture model in our mind is a categorical distribution over a space of measures. So like a Gaussian mixture model is simply a distribution over Gaussians. In order to generate a sample from that space, we sample a mixture component, one of the Gaussians, and then we sample from that Gaussian component. And we like to estimate the mixture that describes the data we observe. There's a notion of identifiability with these problems, which is if there is a true mixture in some sense, is it the only mixture that would describe our data that we observe? And this is true for Gaussians. No Gaussian mixture model looks like any other Gaussian mixture model when you observe data. So we say, well, what if we get rid of this assumption that it's Gaussian and we say it could be any possible mixture component? Well, we need to make some other assumption which sort of allows us to get a grip on the problem. And we say, well, instead of sampling a mixture component and only sampling from it once, what if we sample from it n times? So we have more data from each component, but we don't know which component it's from, or even the set. We have this set of components is very large in this case. And we have a notion of how many samples do we need per these groups of samples in order for our distribution to even be uniquely identified, or what we call unidentifiable. We call it unidentifiable if the true mixture model is the simplest one that describes our data, and we call it n-determined if it is the only mixture model that describes our data. And we have some nice results. We say that we found that any mixture model with m components is identified with 2m minus 1 samples per group, and this was actually a result shown before by Rabbani and others, but I think our proof is nice, and that with 2m samples per group, our mixture model is the only mixture model that describes our data, and that is new as far as I know. Again, both those bounds are both tight. Also, if your mixture components are linearly independent, then 3 samples per group is enough to make it the only mixture model that describes our data. And if your components are jointly irreducible, you only need 2 samples per group to describe your data. And these are all like generalizations or strengthenings of previous results. There's a lot of math over here, which I won't get into, but it relies on basically transforming our measures into a Hilbert space, which allows us to do nice geometric arguments. And we also have algorithms and such, which are not demonstrated on this poster. That's it.